All right, so let's talk about integration by parts. So what I'm going to do in this video is I'm going to start off just talking about what it is, what the formula is, what to look for, and then I'm going to do a really in-depth example, kind of over-explaining every step, just to use it as a kind of teaching tool, and I call that example 0. And then after that, I'm going to go through some example problems a lot quicker, a lot more normal paced. And if you just want to see those examples, I have a timestamp in the description that'll skip all this beginning explaining part. Right? But for now, let's just jump into it. Right? So what is integration by parts? Integration by parts is one of the two main techniques for integrating more complicated formulas. In whatever class you're in, which is most likely your first or second calculus class, you should have already done U substitution, which is the other technique. And if you haven't done U substitution by this point, I highly suggest I have a video on it, you can go watch that. I highly suggest you know that beforehand because it is a much easier technique, and the substitution technique, I guess you would call it, is similar to the method involved in integration by parts. All right? So what integration by parts is the way U substitution undoes chain rule. Integration by parts is meant to undo product rule. So the way in U substitution, you look for, when I'm doing this integration of this like more complicated function, is there an inside and outside part? For integration by parts, what you look for is, are there two things being multiplied together the way I would look for in product rule, right? That's kind of the telltale sign for that you're using integration by parts. So what is the formula? So it's the integral of u dv is equal to uv minus integral of v du. Now there's a way you derive this and why this works the way this does, but that's not really relevant to actually doing the computation. And I'm going to go through example 0 just to show how to apply this formula. Because what we're doing is we're taking certain components of this formula, setting one component equal to u, a separate component equal to dv, and then finding out from u what du is by deriving, finding out from dv what v is by integrating, and then using these variables to find out our final answer. So I think it'll become more clear once I go through example 0. So what do we have here? We have the integral of x times e to the x dx. Our first step is to assign something to our u and assign something to be dv. Now, I'll go over in a little bit after example 0 how you really determine what should be u and what should be dv, because that is the most difficult part of this type of process. But let's just talk about the computation first. So I need to find a u, and I'll write it off to the side here. And then I also need to find a du based off that. I'm going to need a v, and I'm going to need a dv. So first I need to assign one of these to be my u. In this case, I'm going to make my u equal to x. And that would mean my dv should be e to the x dx, the thing that's left. All right, and from here I need to find, what's my u then? Well, what's the derivative of x? Derivative of x should just be dx. What is the integral of e to the x dx? Well, that's just e to the x. Now that I have these components, I can actually substitute using this formula, right? So since my x became u, right, I can I'll actually write it to the side here. I can rewrite this as the integral of u, and my e to the x dx became dv, which is the form we want. That all should be equal to, I'll just write down here, u v minus the integral v du. And we just substitute the the values we found before. So what was u? U was equal to x. What was v? V was equal to e to the x minus the integral. What was v? That was e to the x. And what was du? That was just dx. And what we need to do is just finish off this integration. What's the integral of e to the x? The integral of e to the x is just, or e to the x dx is just e to the x. E to the x plus c, right? We need to add our constant of integration because we are not doing a definite integral. And it's as simple as that. That would be our final answer for this integral. Okay? So now let me talk about how to choose what should be u and what should be dv. So this is going to be the hardest part of integration by parts because it can be kind of complicated. That's a tricky question. How do I know what to substitute? And there was a very similar question asked when doing u substitution. So there is no correct answer. There's no like one specific way to do it every time. It depends on question to question. So let's look at, I think I have a pretty straightforward kind of guide to use, right? So we'll have 3 columns here. And this is kind of how I want you to look at each thing. In this first column, we'll just have all things that are easy to differentiate, right? So all things easy to differentiate. In this column, we'll have everything that's easy to integrate. And then here is just stuff in the middle that, you know, you could differentiate them pretty easily. You could integrate them pretty easily. Now, the way this works, we want to find a dv that's easy to integrate and u that's easy to differentiate, right? Because we assign a dv and we need to find v. So we kind of want to make this easy on ourselves by finding a value easy to integrate. E to the x, super easy to integrate. It's just e to the x. This is just like an x term. X terms are super easy to differentiate because they just become 1, right? That's why I chose those the way I did. So things that are easy to differentiate, logarithms. Logarithms will almost always exclusively be what you make u. Things that are easy to integrate, exponentials. Anytime you have an e to the something power or anything like that, exponentials are some of the easiest things to integrate. That's what you're going to make dv. And then there's stuff in the middle, like polynomials. Right? Now, when you have polynomials, you could integrate them, you could differentiate them. You know how to do both. So how do you determine which one you do? Well, that depends on what else you're given. If you have a logarithm and a polynomial, the polynomial should be the thing you integrate, logarithm's the thing you'll differentiate. If you have a polynomial and an exponential, the polynomial should be what you differentiate, while the exponential is what you integrate. Okay? Hopefully that is kind of a much more clear explanation of how to choose what becomes u, what becomes du, and let's hope that makes the problems a little bit easier. So let's look at the first example. So our first example says integral of x times ln of x dx. Our first thing, we have to actually do our substitutions. What is going to be u? What is going to be dv? Now, like I had here, we have a decent way of determining which should be which. Since we have a logarithm, right, the natural logarithm, that should be the thing we want to take the derivative of. So that's an easy choice for what we're going to make u. So u is going to be equal to natural log of x. And then what would du be off of that? That should be a memorized derivative. Du should equal 1 over x dx. And next, we have to determine what our dv is, and that should be the other term that's left. So our dv is going to be x. So v is something we'll figure out. dv is equal to x. Integrating x, not as easy as differentiating it, but still shouldn't be too much of a problem. We should get v is equal to 1/2 x squared. And integration like that, you should really be able to do super quick, super snappy by now. All right, so now let's put it into our formula for integration by parts. So this should all equal uv minus the integral of v du. And now we just take these values over here on the right and substitute. So u is going to be equal to natural log of x, and v will be 1/2 x squared. So that gets me 1/2 x squared ln of x, and that can just stay up front, subtracted by the integral of v du, which is 1/2 x squared, 1/2 x squared times 1 over x. Dx. Now we can simplify stuff here, right? So we'll just do that just to make the integration a lot easier on us. So rewriting this ln x down here, 1/2 x squared times 1 over x should just get us x squared over x dx. And that's actually super simple because these will cancel. And we're just left with an x dx on this side, right? So from here, 2, an x over 2. My bad, I forgot to multiply the 2 to the denominator. So what we're left is, by bringing the 1/2 to the outside, right, you're able to bring constants to the outside of an integral. Important rule to remember. It'll save you a lot of time later on. 1/2 integral of x dx. Integral of x, pretty easy to compute. And that should be equal to 1 over 4, because integral of x is 1/2 x squared. 1/2 times 1/2 is 1 over 4. And then x squared plus c. And that would be your final answer. All right, let's look at another example. All right, so in this example, we have the integral of 3x plus 5 times cosine of x over 4 dx. So we see two things being multiplied together and we're asked to integrate. So this is just a clear example of when to use integration by parts. So now we have to determine what is going to be u and what is going to be dv. Now, typically the thing that's harder to integrate should be the thing that's u, and the thing that's easier to integrate should be dv. In this case, they're both on the same level of which one you would rather integrate or differentiate, right? I can integrate both of these pretty easily, and I can differentiate both of these pretty easily. So just out of personal preference, I would rather take the derivative of this than take the derivative of this. So I'm going to make u equal to 3x plus 5, right? So this just goes to show there's no hard and fast rule, right? Just leave a little room here. So u is going to equal 3x plus 5. So what would du equal? Pretty easily, that would equal 3 dx. Never forget the dx. Super important. Next, what is v and dv? So dv is going to have to be my cosine x over 4 dx. Cosine x over 4 dx. And in order to integrate that, what's the integral of a cosine? We're going to get sine, and because of the x over 4 here, we're going to get on the outside a 4 cosine, or sorry, 4 sine, that's meant to be a sine, x over 4. Okay, and those kind of integrations should be pretty quick at this point. If you need practice on those, just go get a bunch of problems on simple integration techniques for sine, cosine, for single term things. All right, so now that we figured out our u, du, our v, dv, we just read out our formula and make our substitutions. Okay, so we know our formula is going to be u, v minus the integral of v du, and I'm just going to start substituting, right? So u is 3x plus 5, so that's going to be 3x plus 5, multiplied by v, which is 4 sine x over 4. 4 sine x over 4. And that's going to be subtracted by the integral of whatever's in here, which is going to be, what is v? V is 4 sine x over 4. Multiplied by du, which is this, 3dx times 3 dx. Now I'm just going to rewrite this. Anytime you see constants inside of your integral, bring them out. All right. So this 3x plus 5 and 4 sine x over 4 stay there, minus 4 times 3 is 12. The 12 gets taken out. So then we're left with the integral of sine x over 4 dx. And the sine of x over 4, if you integrate that, you should get negative 4 cosine x over 4. All right, and what that leaves you with, 4 times 12 is 48. So we get 3x plus 5 times 4 sine x over 4 minus 48 multiplied by negative cosine. So that would turn this positive, so I'm just going to write cosine x over 4 and plus c. Right? So hopefully that example made sense. It was a little more complicated than our previous examples. So those are 2 examples of doing indefinite integrals, but those are not the only things you're going to do. You're going to need to do definite integrals. So let's work on the next 2 examples, which will be evaluating between an upper and lower bound. All right? So what I've written up here is kind of a modified version of our integration by parts formula using definite integrals. So we have these bounds a to b. All you're going to do is you're going to have to evaluate that first uv from a to b, and then you would do this second half of the equation, that integral, the way you would normally any definite integral. Let's look at this example. Here I have an integral from -1 to 2 of x times e to the 6x dx. All right, so starting off pretty straightforward. Now, if we remember from before, right, what our, how to determine what u would be, what would dv be, exponentials are easy to integrate. So our e to the 6x should clearly be our dv, making our x our u term. So off to the side, I'll just write, okay, u is equal to x. making du equal to dx. And now let's find our v and our dv. Our dv is going to be equal to e to the 6x dx. And that would make our v 1 over 6 e to the 6x, just e to the 6x. All right? Now that we have these pieces of information, let's put them into this formula. So uv, u is my x term, so x multiplied by v, which is 1/6 e to the x to the 6x, 1/6 e to the 6x, and that's going to be evaluated from -1 to 2. And that's going to be subtracted by our integral of v du. Now, I'm going to take out my constant because v is 1/6 e to the 6x, so I'm going to write my 1/6 on the outside, something you should really get used to doing. And that's still the integral from -1 to 2 of e to the 6x dx. And all I'm really doing, I'm just substituting in these values. Once you find these 4 values, the problem should become fairly straightforward. Okay, so let's see this next bit. All right, so evaluating this part, fairly simple. You should know how to evaluate a definite integral. Substituting in 1 and evaluating, then substituting at -1 and subtracting those 2 quantities should get you 11 over 36 e to the 12th plus 7 over 36 e to the -6. And I'm skipping like the steps of where I'm writing it all out, otherwise, because if I did, this video would be like an hour and a half long. But yeah, that's pretty much it for doing a definite integral. So, all right, if you skipped the beginning intro part, I suggest you stick around just for this last little bit, just to go over integration by parts is mainly governed by this particular formula. You just have to find the things to substitute. You write them in the corner. You find du, you find dv, you find u, you find v, and just plug them into the formula. Important thing, how to determine what to make u and what to make dv. Simple answer. The things that are easiest to differentiate, easiest to take a derivative of, that is what you make u. Logarithms would be the classic example of that. What do you make dv? What are the things that are easiest to integrate? Exponentials are your classic example of that. And based off that, that's how you determine what you make du, that's what determines what you make u and what you make dv. Now, this is definitely one of the more complicated topics. If there are any questions, throw it down in the comments. Other than that, good luck.